Hello, I'm Dahami, and this is a group project for AI module with Sayuri from the Department of Computer Engineering, University of Ruguna. Our topic is text emotion classification with BERT. To set the stage, let me briefly introduce why this problem matters. Emotion classification helps the system understand how people feel in text, useful for social media analytics, customer feedback, and mental health insights. Traditional methods often miss context, but transformers like BERT capture subtle cues. In this project, we built a BERT-based classifier to identify 6 emotions: anger, fear, joy, love, sadness, and surprise. With that context in mind, let's define the specific problem we address. Emotion in text are complex and context dependent. Like I'm crying could mean joy or sadness. Lexicon or bag of words approaches ignore these nouns. We need a robust model that understands emotional meaning in short English text. Based on this problem, here are our concrete objectives. We aim to develop an end-to-end burst system, apply tokenization and label encoding while preserving. Fine-tune for 6 classes and evaluate using accuracy, a funny scores, and a confusion matrix. To meet these goals, start with the dataset. We use the emotion dataset for NLP, roughly 16,000 train, 20,000 validation, and 20,000 test sample across 6 classes. This distribution is imbalanced, joy and sadness dominant, while surprise is underrepresented. Let's look more closely at how those classes are distributed across splits. Across train, validation, and test, as you see, the distribution are consistent. Joy around 30 to 35%, sadness around 27 to 39%, anger and fear near 11 to 14% likewise. This imbalance will influence performance, especially for the minority classes. These distributions guide our pre-processing choices. We keep text cleaning minimal to preserve semantics. We tokenize with BERT's uncased tokenizer and set a maximum sequence length of 75 tokens. So anything longer than 75 is truncated. Labels are encoded with label encoder, and we build PyTorch data loaders with a batch size of 60. To justify that sequence length, here is the token length view. As you see, the token length distribution shows most texts are short, well under our 75 token cap, so we achieve good coverage with efficient batching. With pre-processing in place, Sayuri will take us through the methodology, results, and key takeaways. Thank you.
So our model is BERT-based with a simple head, like pulled output dropout at 0.3 and a linear layer with 6 outputs. We train with a cross-entropy loss using Adam W at a learning rate of 2 times 10 to the minus 5, and batch size is 16 for 10 epochs on GPU and took about 24 minutes in total. Now, how does this setup perform? On the test set, we achieve about 0.93 accuracy, a macro F1 of 0.88 and a weighted F1 of 0.93. By class, sadness performed best with F1 around 0.97, joy around 0.95, while surprise is the weakest at about 0.73 due to its limited support. So let's unpack what that looks like over training and with concrete examples. Training accuracy approaches 1, while validation accuracy approaching to the 0.94, indicating mild or fitting in a later epochs. The confusion matrix shows a strong diagonal. So the most mistakes are semantically close. Joy and love are often confused both ways, and surprise is sometimes predicted as fear as well. So to make this practical for users, we wrap the model in a simple UI. The interface returns the top emotion and the full class probability distribution. For an input like, wow, it's amazing, the system predicts joy with very high confidence, while other classes remain near to 0, making the output easy to interpret. So, beyond the demo, it's important to acknowledge the challenges as well. So, the data imbalance lowers the performance for minority classes, and joy and love can overlap in language, creating confusion. And the surprise is often mistaken for the fear and joy, reflecting shared cues and few examples. So, these are the main areas where targeted improvements can help. And bringing it together, here is our conclusion where I would like to take this next. We built a robust, efficient based word-based emotion classifier with strong overall accuracy and fun, supported by a reproducible pipeline. Future improvements include handling class imbalance more smoothly and adding early stopping to reduce overfitting time and exploring the LLM prompting and future learning to increase the adaptability as well. So that brings us to the end, and thank you for your time.